Hey, welcome back. Today we're going to be talking about the first law of thermodynamics, and this is useful for a physics or an AP physics or even a physical science class. So the first law of thermodynamics is really just kind of keeping track of energy. Is energy flowing into our system the thing we are interested in, or is energy flowing out of our system? And again, our system is the thing that we are interested in. We can define our system in contrast to the environment, the surrounding environment. And we also know that energy is neither created nor destroyed. It just changes forms and it goes from one object to another, so to speak. So if the system is gaining energy, then the environment must be losing energy. And if the system is losing energy, then the environment must be gaining energy. All right, so let's take a look at our equation for our first law of thermodynamics right here. It's delta U is equal to Q plus W. Delta U stands for a change in internal energy. Internal energy is like temperature, but not exactly the same thing. I've done a screencast on this topic. I'll put a link in the upper right so you can take a look if you like. But basically this is a measurement of the average translational, rotational, and vibrational energy of the particles of the substance here. So it's a little complex, a little technical, but it's really not that bad once you get comfortable with it. Q is going to be representing heat, and that is thermal energy flowing into the system or out of the system. So heat is always transferring from one object to another, and it naturally flows from the higher temperature source to a lower temperature source because those particles are going to come to thermal equilibrium if you allow for enough time. And lastly, you've got work here. And work, we could say in the context of like a gas inside a cylinder, that would have to do with compressing the gas in the cylinder or having the gas expand in the cylinder, thinking of work being positive or negative in that sense. So we're going to take a little more of a deep dive into the first law of thermodynamics. I do want to say at the outset, though, that there is an alternative way you can write the first law of thermodynamics. I happen to like this way, and so does the College Board. So I would argue that this is more important to learn because I think it's also more consistent as well to learn this in terms of the concept. So I'm going to teach this, but I am also going to explain the thinking behind this version of the equation. So if you have this version of the equation from your instructor, no worries. We're going to get to how to think about that. All right, so let's get to it. So the big idea for the first law of thermodynamics is to think about the question, is energy being added to the system? And if the answer is yes, the Q, the heat, or the W value, which is work, will be considered to be a positive value. So it's really just a way of bookkeeping, a way of keeping track of energy. And if the system, which is the thing that we're interested in, gains energy, we're going to call it positive. And if energy leaves the system, we're going to call that negative. Why I like this version of the equation, it's pretty consistent. That's the principle, and the principle makes things pretty easy. All right, so let's take a look at an example. Let's say we're going to add heat to this system right here. First of all, what would be our variable, and would it be positive or negative? Well, our variable is going to be Q, right? And it's going to be positive because the system is going to be gaining heat energy. And by the way that would happen is if this gas inside here was colder than its surrounding environment. Over time, there are going to be collisions on the wall of the container from the environment, and they will have a higher average kinetic energy compared to the particles inside here. And over time, those collisions will even out in terms of the energy. So they will come to thermal equilibrium. All right, well, what about if heat leaves the system? How would we describe that in terms of our variables? Well, we would call that Q, and we would call that a negative Q, actually, because the system is going to lose energy. Well, what happens if we compress the system? And so we're going to call the system the gas particles inside this cylinder, this piston right here. And if it gets compressed, think about it. You're going to have a higher average kinetic energy of particles. They're going to be bouncing around with more collisions per second as they are crunched together, you could say. So that means the system is going to be gaining energy. And if the system is gaining energy through a force applied over a distance, what do you think a force applied over a distance is? Well, hopefully that sounds familiar as work. And so we could say that this is going to be a positive work because the system is going to be gaining energy. All right, well, what about if the system expands? The system is literally pushing back on its environment. And if the system is pushing back on its environment, it must be losing energy in the process. It itself is doing work, so that means it's losing energy. All right, this right here is a summary of what we have just talked about. So if you'd like to pause this and read it, go for it. Otherwise, I'm not going to read at you right now. I'm going to continue with our examples. All right, so here's an example here. So it says the internal energy of a system is initially 55 joules. The system does 22 joules of work and gains 11 joules of heat over the time for this process. What is the final internal energy of the system? So this is the first law of thermodynamics right here. And let's think about what we know and what we're looking for. We're looking for the final internal energy of the system. So what we can do with any delta situation, we can break apart a delta, right, and get final minus the initial. And so that's what we're going to do right here. And we are looking for this. So I'm going to add a U initial, internal energy initial, to both sides of the equation to cancel it out on this side over here. So now we're going to say the final internal energy is going to be equal to the heat added to the system, the work done on the system, compressing it, and that is all summed up along with the initial internal energy of the system. And I think that makes sense. We're just keeping track of the amount of energy that this thing has. And those are the logical ways it can gain or lose energy. So then we can go ahead and plug in our numbers, and notice the math is pretty trivial except for, take a look at this, figuring out what signs we have, whether things are positive or negative. In this case, this work is negative because the system does this work. That's really important. It's not work done on it, it's done by the system. That means the system is pushing against its environment. So it's kind of like on that downstroke right here, the piston right here. So it's pushing on its environment, doing work. That means it's losing energy in the process, the system is. And so that needs to be accounted for as a negative 22 joules. So then we just are careful with our sign and we get our answer of 44 joules. Okay, so now what I'm going to do is compare and contrast that common version of the first law of thermodynamics with another version of the first law of thermodynamics that is actually kind of common itself. So this first method that I taught you is the same one that the College Board uses for AP Physics, where it's delta U is equal to Q plus W. I'm going to circle any differences between this example up here and what's going to be down here, the alternative way of looking at the first law of thermodynamics. So it actually depends on your teacher. All right, so notice I've got a plus W, delta U is going to be a change in internal energy, Q is heat added to the system. These two things are true for both examples. Work is going to be considered to be positive if it's done on the system. And the principle here is positive variables if the system gains energy. So ask yourself, is the system gaining energy? Like think about a gas that's being compressed. Those particles are now smashing together more often, more collisions per second, and they're gaining kinetic energy as they were smashed together. And in that case, you could say that there is a positive amount of work. Well, fair enough. So then you could say, well, what's the alternative? The alternative is this, delta U is equal to Q minus W. So some authors and some instructors use this version, and the difference is that they're considering work to be positive if it's work done by the system. Not on the system, but by the system. So the principle here is going to be different. It's a point of view of what work the system does. So it's almost like personifying the system. Like if you had the point of view of that gas, and you were pushing back on your environments, and that is considered to be a positive thing, then maybe that's the idea to carry forward. So we could say the principle is the point of view of what work the system does or heat it gains. So heat is going to be the same, Q is going to be the same for both. The key difference is going to be work. So I would suggest you ask your instructor which version you're going to be using, or look at an example to see which version you already are using. I think this is the more common and the easier one to learn. All right, one last thing. And so down here, ask yourself, is the system doing work or gaining heat? If so, we're going to call that a positive value. And so, yeah, that's how you would go about doing this. Now, I'm going to do a part 2 to this lesson where I talk you through the equation for an expanding gas, for a change in volume, and how that is a form of work, either done on the system or by the system, and how to keep that all straight in your mind. So stick around for the next lesson. If you have any comments down below, let me know, and I hope you all have a great day. Take care.